we left off last time. So just to remind you what we were doing, we were talking about constitutive relationships. And that word constitutive is just a fancy word that means the relationship between stress and strain in a given material. And it can be a rather complex relationship. It can, for example, be a nonlinear relationship. You can have plasticity. You can have nonlinear elasticity. You can have temperature dependence. You can have moisture dependence. These relationships can be relatively complex. However, what we went through last lecture was just a sort of a thought exercise based on your past experience using constitutive relationships. And we saw that in that thought experiment, we could sort of think through the most simplistic constitutive relationship. That's what we call the linear, elastic, isotropic constitutive relationship. And the result of that thought process is actually here. And what we have is a relationship between stress and strain, now written in a matrix representation of the tensor relationship. So you have to remember this is a tensor relationship. The terms on the left-hand side, we have, on the left-hand side, we have 6 stress components shown here. On the right-hand side, we have 6 strain components. Keep in mind, of course, that we're showing only the unique stress components, but the tensor actually has 9 components in it, 3 of which are not unique. Same with the strain components. And so conceptually, you could also see this 6 by 6 matrix shown as a 9 by 9 matrix. Those are other ways that you can represent the same relationship, but this is, I would say, perhaps the most easily and readily understood way of representing this relationship. A set of 6 stresses that are related to a set of 6 strains through really these 36 coefficients, of which there is going to be symmetry to this matrix. If the right-hand side is presented correctly and the left-hand side is presented correctly, you're going to have symmetry in this matrix. And so instead of having 36 components or 36 unique coefficients within these matrices, you could have as few as 21, or we'll never have more than 21 due to the symmetry. And in fact, it comes down to actually only having 2 unique components. And as you can see in this set of equations, the unique coefficients are the modulus E and the Poisson ratio nu. And so E shows up really only once, and then nu shows up a number of times in this representation as you have it shown here. Now, this entire term here multiplies the matrix. So really, in all these cases, there's an E along all of these components. But, you know, obviously, it's just multiplying the entirety of the matrix. And then we said we could use the so-called Lemay constants just to make this a little bit more compact, but really functionally it's not any different than the equations up above. And so we won't really focus on that. In fact, we're not going to use the Lemay constants at all through the rest of this course. It turns out that that becomes something we'll use more extensively in the advanced structural mechanics course that's going to be offered in the spring. You probably recall from last time, but I also mentioned the shear modulus. You know, when we went through our thought experiment and we looked at the shear stress and its relationship to the shear strain in isotropic material, we defined a coefficient G, which was a proportionality between shear stress and shear strain. And it turns out that that is related to the Young's modulus and the Poisson's ratio. According to this relationship, G is equal to E over 2 times the quantity 1 plus nu. So really, of the 3 coefficients that you've seen, the Young's modulus, the shear modulus, and the Poisson's ratio, for an isotropic material, only 2 of them are unique. Now, you may ask, well, what materials are isotropic materials? Turns out that many of the materials that we use in aerospace engineering are or can be reasonably approximated as isotropic. So you can think of this as being most metals, aluminum, steel, copper, brass, titanium. Inconel, all the high temperature alloys that we sometimes use in supersonic flight vehicles, I should say almost all of them, behave as isotropic materials. So if you know the Poisson's ratio and you know the Young's modulus, then you have a sufficient amount of information to describe at least the linear portion of the material's stress-strain response. Now, again, this relationship that we've written, in general, the matrix that you see here now could be, as I mentioned earlier, a function of temperature. It also, importantly, can be a function of strain. And when, the simplest way to represent that is if I write a normal strain, which I'm going to call epsilon there, and a normal stress, sigma, okay, the modulus E is a linear relationship. And then there's a nonlinear relationship that can occur after that. But we can, if we never have any yield, if we never load our structure past yield, then it's reasonable to model it simply with this linear elastic relationship shown in these matrix equations. And then typically what you're going to do is if you have a material that ultimately does yield, and you're doing some sort of structure that's loaded so heavily that it goes into yield or could potentially go into yield, then you're typically using something like the finite element method in order to enforce the plastic portion of this curve rather than the linear elastic portion of the curve. So in many circumstances, when we're talking about the relationship between stress and strain and we're doing hand calculations, largely that's going to be limited to the linear elastic regime where the moduli, that's Young's modulus or shear modulus and Poisson's ratio, is likely sufficient. And then you're calculating how much stress occurs and basically evaluating whether it stays under yield or exceeds yield before you continue to do more advanced calculations if you need to. Okay, so another thing that's worth noting is that there are many other material descriptions. That is, isotropic materials, the metals that we use, are just really a limited subset of the available engineering materials. And in fact, they're a limited subset of the materials we use in aerospace engineering for our flight vehicles. Now, when I said there's two constants, that's sufficient to describe an isotropic material. The limit in sort of the most complex linear elastic material that you can encounter is something called an anisotropic, fully anisotropic material that can have as many as 21 constants. Now, where does 21 come from? That comes from that 6x6 matrix where you're now only counting the portion that's above the diagonal, inclusive of the diagonal. So there's 6 on the diagonal, 5 on the row above, 4 on the row above that. And if you add all of those up, you get 21 constants. Across the other side of the diagonal, there's symmetry to the matrices. So it's not going to be 36, it's just going to be 21. And so it's worth noting that there are materials that fit between this fully anisotropic 21 constants and the so-called isotropic materials, and that just have 2 constants. So let me name them for you, or at least one that's really critical to us in the aerospace world. If you hear the word orthotropic materials are materials that behave in such a way that they have really 9 elastic constants that are unique. And in the frame that we're describing them, they still have a large number of zeros in their constitutive matrix. So what does this mean? What does orthotropic mean? Really, you can think of this as being something like a long fiber reinforced composite material. In fact, I'll wager all of you probably can look down at the clothing that you're wearing today, and you can pull on your shirt. You know, your shirt is going to be a woven material, and you can find that if you pull it, let's say, horizontally, it'll behave one way. If you pull it vertically, it'll behave another way. And if you pull it at 45 degrees to that, it'll behave yet a third way. And so when I'm saying that, this is something you can like physically experience right there in front of you, where the response of the material, the constitutive response, that is the response that relates the amount of stress that you have to apply to get a given amount of strain, it's now a function of which direction you are loading the material. A function of direction. So in this example, if we had a long fiber reinforced material and the fibers were all oriented with respect to the x direction, like so, we didn't have any transverse fibers, we'd get a very stiff modulus in the x direction. By the way, these are bound together by what's called matrix. The matrix is typically an epoxy. So it's like a glue, essentially, that's holding all those fibers together. So if you're pulling in the x direction, it's going to be relatively stiff because those stiff, strong fibers are aligned with that direction. If you're pulling in the y direction, you're going to get a different modulus, typically going to be lower because there are no fibers directly opposing that direction of loading, and so the glue or epoxy that happens to be there typically is not as stiff as the fibers, and so you're getting more strain for the same amount of stress. And then lastly, of course, you could pull it out of plane. In this case, we would have yet a third response, or perhaps the response in the third direction would be quite similar to the response in the second direction. Anyway, as a general statement, it could have a third modulus in the z direction. And then you have Poisson's effect still governs, but it governs with different coefficients. And in this case, what you'll find is that you can have 1, 2, 3 unique Poisson's ratios. So we have 3 moduli, 3 unique Poisson's ratios. There's still symmetry here, so that this combination nu xy over exx is going to be equal to the nu yx over eyy. So these are not unique coefficients on the other side of the diagonal anymore. So in the top left 3 by 3 matrix, we end up with 6 unique coefficients. And then, of course, following down the diagonal, we can have 3 different shear constants as well. So this material is called orthotropic. It's because you have orthogonal planes that all behave differently. And again, it's describing typically long fiber reinforced composites that we use in aerospace engineering, and requires as many as 9 constants. Here's the statement that I already made. Due to that symmetry, of course, we're going to eliminate 3 of the constants that were present. If you count it up in this matrix, this 6 by 6 matrix, how many coefficients I wrote down? I wrote down 12 of them. But here we have 3 symmetry equations, which eliminates 3. So that's how we got down to 9. And as I said, this is typical of a composite, long fiber reinforced composite material. These materials are very broadly used now in aerospace engineering. Every fighter jet in the current 5th generation fighter is predominantly composite material in its primary structures, at least those that are not associated with the engine and the thrust that's generated. The heat, the really high temperature stuff still tends to be very high temperature metals as opposed to carbon fiber. But most of the remainder of the structure is made out of carbon fiber or similar. So this material description, 9 coefficients, is very important in aerospace. 787, the A350, many of the newer light general aviation aircraft are all made out of materials that follow this material description. By the way, it's notable that your body tends to be reasonably well described. Many portions of your body, I should say, particularly bone and some soft tissue, is well described as an orthotropic material. There are other named materials. In fact, this really is all the possibilities that exist out there. You can have a material, depending on the type of symmetries that exist, it can be monoclinic, which has 13. Orthotropic, that's the one we spent a little bit of time talking about, that has 9 constants. Tetragonal, which has 6. Transversely isotropic has 5, so this one's pretty important in composite materials as well. So unidirectional composites, orthotropic, this can be multi-directional composites. Unidirectional composites tend to be transversely isotropic. It only has 5 constants. This means that within a plane, there is some symmetry. And I'm going to try and draw that for you. Okay, so imagine, you know, in the prior drawing, I drew a whole bunch of horizontal fibers. Basically, we were looking at a sheet, looking down on a flat sheet of composite structure. Now, if you took that flat sheet and you looked down its end, sort of like looking at a tree trunk almost, you know, you'd have this structure that has little fibers coming out of it, like so. And because of that configuration, you get this plane of symmetry where everything, you know, it doesn't really matter at what angle theta you rotate this plane. The material in plane is going to behave the same, whereas the along fiber direction is going to be unique. So that's a transversely isotropic. You need 5 constants to describe that, as opposed to a fully orthotropic materials. So transversely isotropic, very important. Orthotropic, very important. And then, of course, lastly, what I don't have here, that was isotropic, right? So that's also very important. Now, what's unique about isotropic is that it doesn't really matter which coordinate system you look at it from. It's isotropic. It only requires 2 constants, and it behaves essentially identically irrespective of which orientation you apply the loading. You know, if you take a piece of aluminum, you know, a big billet, which is a block of aluminum, and you machined a specimen that was predominantly horizontal, and then you tested that, or if you machined one that was predominantly vertical, and then you tested that, or one at 45 degrees, and then you tested that, isotropic would always behave the same. Its stress-strain response would be the same, whereas transversely isotropic, or you know, orthotropic, if you cut it along the fiber direction and pulled that coupon, it would give you one response. If you went at 45 degrees, it would give you a different response. If it went at 90 degrees, it would give you a different response. So all of the materials except isotropic now depend on the actual magnitudes of the coefficients, depend on your defined coordinate system. So as you rotate coordinate systems, be aware that the relative magnitudes of the coefficients change. And in fact, if you rotate this into a different coordinate system, the actual rotation of that can drive these coefficients that are 0 to be non-zero in other orientations. And what does that mean? That means that there might be some coupling between, so if the 0 becomes non-zero, then there would be a relationship between epsilon xx, that's the top row, and sigma xy, that's the last column. So if this, through a rotation of your coordinate system, becomes non-zero, you can get this coupling between normal stress and shear strain, or shear stress and normal strain. You'll get into the details of that with much more vigor if you take the advanced structural mechanics class that's going to be offered in the spring. I'll pause here for just a minute and take any questions. I have not been actively monitoring the chat window, so I'll open that up. I'm not seeing any messages other than a question about the homework. I think that was up before I even arrived, so I'm assuming that was a discussion amongst students rather than with me. Or if somebody wants to ask that question, they can hang out for a few minutes after lecture. Okay, so, keep in mind now that, I represented, let me go back just one or two slides again. So what did we represent? We were representing a relationship between strain and stress that was representable as a coefficient matrix, in this case 6 by 6. You could invert this relationship so that stress was on the left-hand side and strain was on the right-hand side, and that is functionally inverting the 6 by 6 matrix. Okay, you guys probably know how to do that from your linear algebra days. But another representation or another description is this more compact notation. And the whole thing is generally referred to as Hooke's law. So Hooke's law itself was this proportionality between a load and a displacement. That was his 17th century law, was just a proportionality between a given load and a resulting displacement in a material. Generalized Hooke's law now incorporates the fact that you've got a 3 by 3 or really a tensor 9-component strain. You've got a 9-component stress. And in actuality, what you have here is a rank 4 tensor. So it's a 4th rank tensor 3. This is a 3 to the power 4 coefficient. So really there's 81 coefficients, which we in this class will be representing by that 6 by 6 matrix. But in general, if you did the most general description of that, you could represent it as 81 coefficients, of which 21 could be unique and as few as 2 must be unique. Okay, so I kind of showed this to you previously, this table. I'm going to show it to you again. So, the question then becomes, we have at every point in the structural body that's being loaded, at every point in the field, there are 18 unknowns, of which 15 of them are unique. Okay, so we have a linear momentum. This is the sum of the forces. We have angular momentum, which turns out to drive the symmetry of the stress tensor. We have so that one is, in some ways, we've already used that equation. We've got the constitutive law, that is a relationship between stress and strain, which was represented by a 6 by 6 matrix. And a 6 by 6 matrix, there are 6 rows in it, so that's 6 equations. We have the kinematic relationship, that's the relationship between strain and displacement, and that there were 6 of those. So for a total of 18 equations to find the 18 unknowns, 15 for 15 unique unknowns. Okay, so that's our constitutive relationship. Okay, we will now, again, please interrupt me with questions if you have them. I understand that this material can be a little bit challenging, and it's tough to tell staring at, only about 10 to 15 faces out of 50 whether you guys are actually getting this, but bottom line, make sure to interrupt me if you have questions or ask questions in the chat window. Okay, so what we described was generalized Hooke's law. That was a 3-dimensional stress-strain relationship. But it's worth noting that there are circumstances where we can simplify the relationship a little bit. Having that many equations to track at the same time can be challenging, and so it's often where possible we like to simplify the problem. And so I'm sure some of you have heard this term before, or these two terms together, plane stress, 2 words together forming one description, plane stress. So plane stress is a material constitutive description that is a fully 3D description, but with some assumptions based into it. Now, what do I mean by that? Okay, I have here on the screen a photograph of the Boeing 787. That's on the left. Obviously, the aircraft's in flight. And on the right-hand side, and you've seen both of these images previously in our lectures, on the right-hand side is a section of the fuselage of that aircraft. Now, as you're staring at this, one of the things that's quite notable is that the fuselage is large, and this is really, we're only looking at a portion of that fuselage, so you can imagine that this extends to be the complete fuselage. One of the things that's quite notable about it is that its thickness relative to its overall diameter is relatively small. And perhaps more generally, the thickness of this material relative to its, we'll say, width. Now, because this thing's a cylinder, it has, it wraps around on itself. But this principle could apply to something that didn't wrap around on itself, something that's more plate-like or shell-like, if you recall that terminology from earlier in the semester. But anyway, the point is that there's a characteristic length really in two dimensions, and I'm going to draw the other dimension as well. So it's thin relative to this dimension and this dimension. Now, in circumstances like this, what we're going to find is that there is often the case that the out-of-plane stresses, that is the stresses that are sort of oriented normal to this surface that's being generated, are going to be negligibly small. For example, if we look at the outside fuselage of this aircraft and we drew a normal vector here, so this is my attempt to draw a normal vector with a mouse. It's obviously not perfect, but it's oriented away from the aircraft. And at that surface, we're going to have a nearly traction-free surface. Now, there's atmospheric pressure perhaps on the outside, and there's something perhaps slightly different than atmospheric pressure on the inside. So these aircraft are often pressurized. So there might be an internal pressure and an external pressure, but both of which are relatively small. So on the, if we're thinking orders of magnitude, you can think of atmospheric pressure as being, 10 to the 5th pascals, which is a far cry from hundreds of megapascals. So it's 100 kilopascals versus 100 megapascals. 100 megapascals is kind of closer to what the material might fail at. So we're talking on the order of, 100th to 1,000th of the in-plane load that it could potentially carry relative to the out-of-plane load that it is carrying. So in that circumstance, we can have a small stress, or a stress that we're actually going to just say is approximately equal to 0. And in this circumstance, we call that circumstance plane stress. So when a structural body, in this case, as an example, a fuselage, is predominantly loaded in two directions and unloaded in the third, a plane stress assumption can be made. So I'm drawing this isotropic relationship. Okay, obviously that wouldn't apply for the 787, which is a composite structure, but this is a simple description. I think you could generalize. So if you think about the fact that on the inside there's essentially zero traction, on the outside there's essentially zero traction, you can't appreciably build up out of plane stresses in that really short distance. So sigma xx, sigma yy are non-zero, but sigma zz is 0. You could have sigma xy as a non-zero stress, but sigma yz and sigma xz would also be essentially 0, negligible. So this is now the circumstance of interest. What happens? What's different about this plane stress scenario? Okay, now typically when we have a plane stress scenario, we're going to be generally less interested in the out of plane strains. So even though they are not zero, we might not be terribly concerned about what they are, because these are just, often would be something like a Poisson strain. And a Poisson strain, when it's unconstrained, is not generally going to cause a failure. So we might not really be terribly interested in what the magnitudes of epsilon z, z, y, z, and xz are. Now, out of the corner of my eye, I saw a question. So Nicole asked, can you explain what out-of-plane stress is again? Yeah, so the out-of-plane stress, let me go ahead and take you back this one image. Okay, so this is a cylinder. Okay, but the arguments are all equally valid for a flat plate. So I'm going to go to the next image. So here's a flat plate. Note it's thin in the z direction. So I'll draw a coordinate system. We're going to say that x is this way, y is this way. And a right-hand rule would require that z would be out of the plane, which I'm going to draw this way. Okay, so now x, y, and z, x and y are in the plane of this structure, and z is in the direction that it's very thin. Now, plane stress means that we can build up large loads in, say, the x direction. We're pulling it in tension, okay? We could equally be pulling in tension in the y direction, but there's nothing pulling on the z direction. Why? Because, like, for example, that's just atmospheric pressure. So atmospheric pressure, 100 kilopascals, going to be very small compared to 100 megapascals, which I might be pulling in the x and the y directions. So these magnitudes, sigma xx, sigma y, are large. The out of plane is small, on the order of 100th or maybe 1,000th of the in-plane load, so we're just going to effectively call it zero. Now, when we've done this, it turns out that, again, so as you stare at this set of equations, we see that I argued there were reasons we didn't really care what the magnitude of epsilon zz was. Let me go back just so you can see that. So I said these three strains on the left-hand side that I've underlined are not typically going to cause failure, because any strain that may exist is essentially just due to Poisson's effect and is going to be at no stress in that direction. And so we may not need to calculate how much strain is present there. We don't need to know how much thinner that material might get, because it's going to be a negligible effect. And so we maybe don't even track that anymore. We just drop the set of equations. Functionally, what we're doing is we're sort of crossing out this equation, crossing out this equation, crossing out this equation, because we're not interested in epsilon zz, yz, and xz. And then we can cross out column 3, so up and down, cross that one out, cross this one out, cross this one out, because all of any coefficient that was in those columns is multiplying 0. And so what we get now is a smaller subset of the equations where the interesting stresses, sigma x, x, y, y, and xy, the non-zero stresses, still remain in our constitutive description. The interesting strains are going to still remain. And what's left in here is now just a 3x3 matrix of coefficients that, basically what we're doing is we're saying only 3 of the equations are now of any concern to us. We're neglecting the other equations in some sense, with the exception of when we're inverting the equations, we need to make sure that we track it so that those stresses remain 0 irrespective of the strains that result. And so in the end, what we have is, so we have now a subset of the matrices So this is the C matrix. I'm sorry, this is the S matrix. The compliance matrix is the top one, which I'll just box. The blue one is the compliance matrix. And now it is, in this limited circumstance, can be represented by a 3x3 instead of a 6x6. And the C matrix, which I'll just do as vertical bars here, in this subset where the out-of-plane stresses are approximately 0, we can represent this constitutive response with strain on the right-hand side. This is now the C matrix, matrix of coefficients, constitutive coefficients, going to be 3x3. Okay, and hopefully that makes the problem easier. We neglect calculating anything that's not here under that limited set of circumstances, and it just simplifies our work. Okay, there's another circumstance that is two-dimensional that is interesting, and that's what we're going to call plane strain. Okay, plane strain. And I came up with this example of plane strain. Now this is a circumstance you maybe are less familiar with, but it's nevertheless something that we encounter in aerospace engineering with some regularity. So plane strain, let me skip ahead to the next slide here. Now this one you're going to have trouble seeing. For some reason I couldn't get this to fit on the screen, and I apologize about that. You've seen this equation before, and of course the right-hand side of this equation is going to be a vector of length 6 with strain in it, right? So I'll just go ahead and say that that is way over here on the right-hand side. Now what's important is we have the analogous circumstance where in the third direction, because of the geometric circumstance, you can have a circumstance where plane strain exists. That means that in your, you can have 1, 2, 3, I'll say epsilon xx, we're going to have y, and then zz. In this case, zz is going to be equal to 0. We have no extension in that third direction. And then similarly, we'd have a 0, 0, and then epsilon xy. Okay, so this is way over on the right-hand side. And now in this circumstance, you might ask, well, when does this circumstance arise? Why in the world would you ever have a circumstance where the out-of-plane displacement and strain are constrained? Okay, it turns out that that actually does happen with some regularity, and that's kind of one example is this image that I'm showing you here. So it's becoming more common in the aerospace world to actually use adhesives to bond things together rather than fasteners. It has some benefits, improved load transfer, less stress concentration, lighter weight, and therefore, because of all those things, often a longer life. But what ends up happening is you have a, so I'm going to draw something. I'm going to say that here I have this aluminum structure that's kind of stiff, bulky, and then I'm bonding it to another aluminum structure that's somewhat stiff and bulky. And then in between, I have this adhesive. Now, if the aluminum is fixed in place on both the top and the bottom, and it's relatively stiff, I'm saying its modulus might be, say, 70. Aluminum typically has a modulus of about 70 gigapascals, so I'll write that 70 GPa. Whereas this adhesive might only be on the order of 0.7 GPa for its modulus. Okay, so it might be on the order of, you know, a few hundredths of the material stiffness of the Young's modulus. Okay, so in that case, as this material inside is loaded, it's not going to move the aluminum very much. So therefore, the aluminum is going to have these fixed boundary conditions that create a circumstance where there is no strain in the adhesive in that direction, the arrow direction that I've shown. And we're going to call that the Z direction in this case. So epsilon ZZ for cases like adhesives is going to be equal to 0. And similarly, XZ and YZ also are going to be equal to 0. So again, here we have 0, 0, 0 that are enforced in our constitutive response. And lo and behold, when you go through and propagate that into the equations and calculate your new effective C and S matrices, now in 3x3 terms, where you're ignoring the stresses that may be present. You're not. When I say ignoring, I'm saying you're not calculating them. You're treating them as if they exist, but you're not calculating them. You can therefore calculate the stress and the strain using this smaller set of constitutive equations. Again, it simplifies the problem. Okay, I'm going to give you a big old caution here. Okay, this we have to do very carefully, and that's because the out-of-plane stresses in this plane strain scenario can actually be non-negligible. You know, you can get stresses that are 20% or maybe even a little higher of the in-plane stresses as out-of-plane stresses. And so in some circumstances, if that adhesive happens to be particularly weak in that ZZ direction, you can cause that material to fail. In fact, in aerospace, one of the ways that the adhesives tend to be most susceptible to failure is actually in peel. So if you can get those materials sometimes to peel away from each other, and it delaminates, and it can be problematic. Perhaps this is something we need to be a little bit more cautious about when we're making this plane strain assumption than when we're making the plane stress assumption. The plane stress assumption, usually those out-of-plane strains don't contribute to failure, whereas it's possible for the out-of-plane stresses to contribute to failure in the plane strain scenario. So the calculation gets easier, but you still have to use it with some degree of caution. Okay, so I see Amir has asked the question, can we assume plane strain for problems like a lap joint? The answer to that is I'm going to say yes. You can, but as with all things, you need to do it appropriately and be able to justify the assumption. So for what purpose are you making that assumption? And what are the consequences of making that assumption? So as a general statement, I would say that that plane strain would be a pretty good assumption for a lap joint if, and in the limited circumstance of, if that lap joint were long into the depth. Okay, so and going back, what was the lap joint? Some of you maybe missed lecture. I'm just going to draw it again. Okay, so this is kind of what that lap joint looked like. There was adhesive between two. So you're, for example, pulling on a load here and pulling on a load here. Now I drew it two-dimensionally, and the reason why I was cautious when I answered yes is it does matter whether it's thin in the Z direction, as I'm drawing now, or whether it's really thick in the z direction, as I'm drawing now. So if it's very thick in the z direction, then plane strain would probably be a very good assumption, because the stiffness of the lap joint substrates themselves would dominate the strain in that z direction. But if this were really thin, then it wouldn't be a good assumption. So again, these are all circumstantial. And typically the plane strain assumption is going to apply when you're using something like an adhesive, and it's in one direction, it's very long compared to the other directions. So very stiff materials that are oriented very long into the depth. That would be a great time to use plane strain. Plane stress, a great time to use plane stress is something like that fuselage. And note, it's even interesting, you know, that you can use plane strain in a fuselage if you've got an adhesive joint in this cylindrical structure, you know, for the purposes of calculating the adhesive stresses, using the plane strain assumption would be really a great idea. But for calculating the stresses of the sort of parent materials of the fuselage, and neglecting the adhesive, assuming it's doing its job, then plane stress would be more appropriate. So same structure, different aspect of the structure you're looking at, one assumption appropriate for one aspect, another assumption appropriate for another aspect. So always got to use your judgment in these circumstances. Okay, not seeing any more questions. Oh, here's one more. So Nicole asks, so plane strain is if something is thick in one direction, and plane stress is if something is thin in one direction. So as a very simplistic statement, I would say that is generally true. Not always true. You got to be careful, but as a general sort of elementary description of when to use those, yeah. Really, the better description is you know, it comes down to this. It's when it's reasonable to say the out of plane stresses are zero. If you can justify that assumption, then you can usually get away with plane stress. If, on the other hand, it's reasonable to assume that the strains are zero out of plane, then you use plane strain. So those statements are generally true most of the time for thick and thin materials, as Nicole's question asked, but not always. So use your judgment. No, you know, it's also important to recognize that you know, if you're doing something like finite element modeling, if you're running a two-dimensional model of a three-dimensional problem, you're going to end up choosing one of these two, plane stress or plane strain, as a consequence of modeling that structure as a two-dimensional structure. So, you know, when in doubt, use three-dimensional structures. When you can simplify it greatly and get away with using two-dimensional structures, wonderful. But then you have to decide, well, is it more like plane stress or more like plane strain? Okay. Any more questions about that? All right, wonderful. All right, so we've reached sort of the end of our introduction to elasticity. At least conceptually, we've introduced the concepts to you. We haven't really practiced them yet, and that's what the remainder of today's lecture will be. And in fact, it'll spill over to some of Thursday's lecture as well. In summary, what we've talked about so far, we developed a method to solve these so-called boundary value problems of linear elasticity. So stress, strain, and displacement are all fields, meaning they vary as a function of space within the body that is the structure. Okay, We're going to assume they're linear elastic, so they can be described by as many as 21 elastic constants as few as 2. They are a boundary value problem, meaning that the equations govern the interior of the body, but the interior of the body is bounded by a boundary, which is essentially external surfaces on which you can have either applied tractions or some sort of displacement constraint. Boundary value problem refers to the external surfaces and anything that passes into or out of the body in terms of loads. And then a linear elasticity is what governs the internal mechanics of the problem. So this ends up being 18 equations and 18 unknowns at every point in the body, an infinite number of points, in fact. And it can be quite challenging to solve. Now, what we need to do is we must do all of the following. We need to find a continuous displacement field subject to the boundary conditions that exist. So it has to be consistent with displacement boundary conditions that exist. We need to find a displacement field that's describable by a function of position. Okay, displacement itself is a vector of length 3. It has components in the x, y, and z direction. Of course, this all applies also to other coordinate systems beyond Cartesian. We're doing Cartesian. Okay, we said it has to be a continuous displacement field. That means no cracks, no voids. It needs to satisfy the continuity requirements of strain, which we, for this purposes of this class, basically meant no cracks and no voids, right? Otherwise, you'd have new boundaries and you need to reformulate the problem. Okay, so that displacement field itself will result in strain. The strains then given by this set of kinematics, where this, epsilon x, x, y, y, z, z, and then the shear strains x, y, x, z, y, z are given by a set of differential equations of displacement. So epsilon x, x, for example, u comma x, it's partial derivative of u with respect to x plus 1/2 partial u partial x squared plus partial v partial x squared plus partial w partial x squared. Similar for y, y, similar for z, z. Similar for x, y, except now we're seeing some sort of cross-direction derivatives. So it's partial u, partial y. So it's the partial displacement of the x direction with respect to the y direction, plus the partial displacement in the y direction with respect to the x. So u comma y, v comma x, plus, and then we get these higher order terms where we're taking partial derivatives with respect to x and y. And then in all of these cases, really, we have this, this sort of general form of what the strain is. So here we have 6 strain equations calculated from derivatives of a displacement field that has a continuity requirement on it. Now, once you've got that, you still have to have those strains result in a set of internal stresses as described by the material's constitutive relationship. So that's this S and C coefficient matrices where stresses result in strains, strains result in stresses, and those stresses now, which correspond to the strains that we just calculated, need to then follow internal equilibrium, stress equilibrium. So these are internal forces that satisfy equilibrium. And that is yet another set of partial derivatives as expressed here. So 3 equations, 3 unknowns. I'm sorry, 3 equations of equilibrium. Some of the forces in x, y, and z direction lead us to these equations. Partial sigma x, x, partial x, plus partial sigma yx, partial y, plus partial sigma zx, partial z, plus the body force component, something like gravity, is equal to rho times the acceleration in the x direction. 3 equations, internal force equilibrium expressed now in terms of stress. And then those stresses are not unconstrained either. They also have to satisfy the externally applied traction boundary conditions through the Cauchy equation, which relates the stress tensor through a normal vector to a set of tractions on the external surface of the body. So that's 5 things that we need to do: a boundary condition at the top of the 5, a boundary condition at the bottom of the 5, a set of differential equations in the middle, 18 equations, 18 unknowns, infinite degrees of freedom, simple problems, right? Yeah, not so simple actually. These problems are actually incredibly difficult to solve for all but very trivial problems. And we'll do a pretty good series of trivial problems so you can understand and internalize and practice how to solve these problems using closed form solutions. But the vast majority of the world's structures cannot be solved with closed form solutions where we would solve the complete elasticity solution. So it would be actually quite rare that we're solving all of these equations in closed form in the real world. We're going to make some really dramatic assumptions that can greatly simplify the problems, which allows us to make an appropriate set of engineering approximate calculations that get us really good answers that are much more easily calculable than what we would do here with this complete system. Okay, questions? Okay, so either we have 51 people who are fully understanding linear elasticity and we'll just move on and keep going, or we have, you know, a whole bunch of people who've fallen asleep and can't ask questions as a result. I hope it's the former rather than the latter. You know, please, as always, interrupt me, scream at me in the chat window, turn your mic on. I'm fairly confident that of the 50 people in the audience right now, there's got to be at least a few that are confused, and so you know, recognize you're not alone out there, and don't be afraid to ask questions, please. I am going to move on, but bring me back to this if we need to. Okay. All right. So the next lecture, this is really, we're now, you know, a little bit behind. But that's okay. We're going to start lecture 9 now, which is we're going to actually do an example calculation of elasticity theory. That is the stuff that we've been covering over the last several weeks. We're going to go through those 5 things that we need to do. We need to establish a displacement field that satisfies strains, that satisfies stresses, that satisfies equilibrium, that satisfies traction boundary conditions. We're going to do it for a relatively simple structure. Okay, what we're going to do is we're going to calculate the deformation and stress and strain in a beam-like structure, a cantilever beam. We're going to return to this problem over and over and over throughout the semester because it's relatively easy so it helps us demonstrate a lot of concepts. If you aren't looking, I don't know if you're able to see me very well. I know that the slides are taking up the majority of the screen that you have in front of you. I'm holding up a pen. A cantilever beam is a beam that extends from a typically assumed rigid structure. So I am going to say that this beam is kind of like a diving board with a person who is standing on the end, perhaps bouncing, ready to jump, but the other end of the board is fixed into the wall, and that fixation is assumed to be rigid. So this is the type of problem that we're going to start with, and we're going to do a fully 3-dimensional elasticity calculation. Really 2-dimensional, I should say, 2-dimensional elasticity assumption. We're not going to deal with the third direction. Now, it's worth noting the coordinate system that I've set up here happens to be X, Y, and Z, so that X is out of the plane, Y is vertical, and Z is along the length of the beam. In fact, so X is into the plane. I said out, but I should have said in to make sure it's a right-hand coordinate system. And the reason we do this is because many of the equations we're going to develop later for beam theory actually are using that along the beam axis direction as Z. So I'm going to use that here as well. We can ignore body forces and accelerations in this. We're going to do a static calculation and ultimately calculate the stress in this. This solution, by the way, is taken, modified slightly, but taken from a textbook, Advanced Strength and Applied Elasticity by Ergerall. Now, we got to satisfy those 5 things, right? Displacement, strain, stress, equilibrium, traction. To do that, we have to set up the problem. And, I would recommend if you're doing an exam, you should always say, let me define the problem I'm solving. I am solving a 2-dimensional elasticity problem. It's a boundary value problem. And so therefore, I need to identify the differential equations that govern the system and the boundary conditions that constrain the differential equation. And if you've done that, you actually do pretty well in the exam. Usually that's, half the battle, maybe even half or more of the points on the exam can be achieved just by properly identifying the type of problem, identifying the appropriate differential equation, identifying the boundary conditions. Solving is sometimes considered gravy on the exams. I see a question from Garrett. It's an honest admission. Thanks, Garrett. I appreciate it. You say I'm a bit confused, but I'm assuming doing a couple examples will help. I hope so. So we'll return to that comment later. Thanks, Garrett. So let's set it up. So first of all, let's look at the boundary conditions. This is a stress equilibrium equation, are the governing differential equations. We need to find boundaries. Excuse me. So first of all, I'll say the boundaries of this structure are along the left edge, along the bottom, along the right edge, and along the top. And I'm going to ask you, okay, so of those 4 boundaries that I identified, let's look first at the top and the bottom. So this, mathematically speaking, is described by, y is equal to plus or minus h over 2. So I don't know, it's pretty small, but you can hopefully see the cross-section that I've assumed. It's a rectangular cross-section, height h, width b, and I've oriented the coordinate system to be at the centroid. So that's in the middle of h, and so the top and bottom are described by y is equal to plus h over 2 and y is equal to minus h over 2. So at this location, what's the boundary condition? I'm going to wait for somebody to throw it out. Give it a shot, please. So boundary condition. You guys have been doing homework on this. Now these are tractions. Can you identify tractions? Oh, thank you, Amir. So he takes the hint. He says 0 traction. So he's absolutely right. At the top surface and the bottom surface, we've got no stress that's applied. What loads are applied? We see over here a point force P at the end. So that's going to be one of the things we're going to deal with. But at the top surface and the bottom surface, there's no stress. So at y is equal to plus or minus h over 2, we can simply say that sigma yy, that is the stress component normal, is going to be 0. We can say sigma xy, the shear on that top surface, is also 0. And sorry, just let me. Last but not least, we can write the entirety of the traction vector. In this case, it's a 2-dimensional traction vector. T is equal to sigma dot n and is going to be equal to 0. So we can see from this, n is going to be 0, 1, so it's going to be in the y direction. We're going to have stresses that are going to have these components to them. Okay, so the next boundary that I'm interested in is the right-hand side. So in our geometric description, this should be at z equals L. I apologize. I've written it as x. It should be z. So at z equals L, what is our boundary condition? So it's not quite as simple as being zero traction this time, right? Because now, in fact, we have this overall force resultant, which I've described as having a magnitude of P, point force P. Traction is P in the negative y direction. So good guess, Ethan. Thank you for guessing. In this case, you're close, but not quite got it. Okay. It's worth noting that the x or the z direction of the traction, the normal here, there is no stress like so. That is not, that doesn't exist. I've just drawn it. That doesn't exist. So that's going to be equal to 0. What Ethan was getting at is that the shear stress on that face integrated over its area, which I'm going to express as being equal to its width b times the integral from minus h over 2 to h over 2 in the y direction, is equal to minus p. Okay, now this is a boundary condition. This does not imply necessarily that the shear stress is a constant over that area, rather that the integral over the area is equal to that total point force. Now we have yet another boundary condition. That would be at the origin. So at the origin, what happens? Well, do we have the same boundary conditions we had in the other locations? Well, not quite. Is it traction free? No. We'll start with this one. First of all, we'll say because of this rigid connection, we can say that the displacement in the x direction, or z, depending on how you've defined your coordinate, and the displacement in the y direction are both going to be equal to 0. That's rigidly fixed out at the end of the wall. And in this case, I'll make one more statement, and that is the slope. This is the derivative of y with respect to x is going to be equal to 0. So slope would be this type of displacement. So it's remaining vertical. We're not getting this sort of shear change in, we're not getting a dy dx at that location. I see Garrett's asked the question. Thank you for the question, Garrett. Yeah, you can see, and I apologize for this, but the z-axis, which I mentioned earlier, is not consistent with the variable I chose. Okay, so that's my fault. I'll try and fix that and put an update in later in the semester for it to go in the course pack. So yeah, you could change this to z, or you could change this to x. For our purposes, I'm just going to change this to x because it makes things a little bit easier. Then you don't have to make multiple changes. Okay, so these boundary conditions, the displacement boundary conditions, or also called the kinematic boundary conditions, because it has to do with any motions that might be present at that location. So u, v, and v comma x are equal to 0. Another boundary condition, we can look at the x component. So this is the normal stress. We can't say that it's zero because it's not traction free. At least we don't know that it's zero like it was on the right-hand side. On the left-hand side, it's possible that there could be a component, sigma xx, at certain locations on that surface. But what we do know is that the integral of sigma xx over that area, b dy, is going to be equal to 0 because there are no applied forces in the x direction anywhere else in the problem. Another statement that we can make has to do with the fact that we have a large moment that we're generating about this point here. Why? Because at a distance L from that point, we're applying a point force P. So this is a moment. This is functionally can be written as a boundary condition on the left-hand side, where there is a resultant moment at that location that balances out P times L. So that moment equilibrium can be expressed as an integral from the bottom surface to the top surface of sigma xx b y dy. So y in this case is a moment arm. You know, as you're thinking about what's going on here, I'll draw it like so. Here is what we're now calling sigma xx in the variable. Sorry about the confusion with the z. Okay, I'm drawing it as it sort of will eventually show itself to be. We don't know the form that this stress takes at this point in the calculation, but we do know is that relative to the y origin, so this is y equals 0, we can say the distance, the moment arm for some differential stress that's applied right here. So here's, I should say, a differential area, dA, where we have some stress magnitude. So stress magnitude times dA, in this case we can treat dA as the width times dy. So b dy is equal to A, and the moment arm is that distance here, y. So integral from minus h over 2 to h over 2 sigma x by dy is equal to the applied moment. And that's a reasonable boundary condition. And then the last one is similar to the first that we applied for the shear stress on the opposite side. That is, again, that the integral from the bottom surface to the top surface of sigma xy b dy is equal to minus p. Okay, I wanted to remind you of the 2D, this is the two-dimensional version of the elasticity problem. Okay, we need to have stresses that relate to strains that relate to displacements. Stresses must satisfy traction boundaries. Displacement must satisfy displacement boundaries. Equilibrium equations must apply, in this case, the two-dimensional version of those three-dimensional equations. Sigma xx comma x plus sigma xy comma y plus body forces is equal to rho times A. Our 2D plane stress constitutive equation is given by this set of equations. Now you might ask, why not plane strain? And that's a reasonable question. I will highlight here the cross-sectional area, and Nicole had asked, if it's deep, if it's, long into the depth of the plane, is that plane strain? Generally, yes. If it's thin in that direction, it's generally going to be considered to be plane stress. So as a general rule, if we're going to sort of treat this as one or the other, I'm going to choose plane stress since it's relatively thin. Tyler asks, B is the base length of the cross-section, not a body force. Yes, in this case, yeah, thank you. Yeah, Bx and By are components of body force vector, but the magnitude B is just the base length of the cross section. Thanks, Tyler, for that clarifying question. Aiden asks, if we are neglecting body forces as assumed, do the B's just equal 1? In fact, they're going to equal 0. So this will become 0. This will become 0, as will this and this. Okay, so good observations, guys. Thank you. Okay, we're going to state that we're going to use, we have this strain displacement relationship, the strain kinematics. I'm going to make note of the fact that for the purposes of this calculation, we're going to assume that the displacements are relatively small. The strains are relatively small, and so the higher order terms, so this would be plus, I'm going to just write it this way, the higher order terms, this is the squared terms of the strain equation. So those terms go to 0. Okay? And therefore, we can just track the linear terms u comma x, v comma y, u comma y, and v comma x. So how do we actually solve the problem? We need to go through, we need to do all those 5 things, come up with a displacement field, satisfying boundary conditions, that satisfies strain displacement equations, that satisfies stress strain constitutive relationship, that satisfies stress equilibrium, that satisfies traction. Got to do all those things, but to do that, we're going to have to make some reasonable assumptions, because otherwise this problem is just too hard. It's just too hard. So what assumptions, then it becomes a question of what assumptions can we make? Okay, we're going to start with this one. As we look at the geometry, I'm going to say that the beam is not thick. Okay, what does that mean? So as I'm looking at this beam, it's, H is how thick it is. L is how long it is. So I'm going to say L is longer than H. And we already noted that the top surface had sigma YY equal to 0. The bottom surface had sigma YY equal to 0. And because the top and bottom surface are both equal to 0, and because there's not much distance from top to bottom where stress could build up, we're just going to go ahead and say, let's assume, for the sake of our calculation, that sigma YY is equal to 0 everywhere. It's 0 at the top, it's 0 at the bottom, it's thin, it can't build up much, so we're going to assume it's 0. If we've done that, then we can use the first of those 2 equilibrium equations. A body force is already equal to 0. We could also set the accelerations equal to 0. I can say that if sigma YY is equal to 0, then its derivative is also equal to 0. And so what do we see? We see that sigma XY comma X is going to be equal to 0. So let me box that equation. How do we interpret that? The shear stress, sigma XY, does not change as a function of X. Its derivative is 0. Okay. Now, by the way, just cross this out here. Don't think about that. My equation numbering scheme, for some reason, is not propagating into my slides. I couldn't fix it. I couldn't figure out why. So just neglect that. Okay. Now, we can also say that the differential equations that we have, these are the 2 equilibrium equations. I can take the derivative of the first equation with respect to X, and this is what I get, this equation. I can take the derivative of the second with respect to Y, and that's the equation that I get. And having done that, what I have is a set of terms, keeping in mind that the order of differentiation can be changed. This and this term are going to be equal to the same. So what do we see when we do that? Well, since sigma yy comma yy is 0, since sigma yy is 0 everywhere, its first derivative and second derivative has to be equal to 0. Therefore, sigma yx xy has to be equal to 0. Therefore, this term here has to be equal to 0. And therefore, this term here has to be equal to 0. So from all of this, from this simple one statement, reasonably justified assumption that sigma yy is equal to 0, we get that the shear stress doesn't change, and we get that the second derivative of the x stress with respect to the x direction is equal to 0. That means sigma xx can be linear at best. Okay, there we go. I've now stated, this slide just kind of repeats what I stated verbally on the last slide. Okay, by my watch, it is 3:55, so we've already sort of exceeded our lecture time by a few minutes. We're going to stop here. We'll pick up here again on Thursday. I'm going to say that since we didn't get through this example completely, I'm going to defer the homework due date for this current assignment until, well, at least Friday, and I will evaluate once we get through Thursday, so that you guys can have the benefit of seeing this example through to completion before the homework would be due, and then I'll give you some reasonable amount of time after that. So, for the time being, just count on that to happen. I will make that official in the e-learning website pretty soon. Happy to stick around for a few more minutes if anybody has questions. I do have an office hours appointment with one of you guys starting here pretty soon. So I don't have a lot of time, but happy to take a few questions. For those that aren't going to hang around, I'll see you guys on Thursday.
This is Hannah. I have a quick question about, so for when we're at x equals 0 for the shear stress, do we assume it's the same as at the opposite end because it's equal and opposite? Or why do we assume that if it's not applied at that location?
That's a great question. And well, let me see if I can find some space on a screen to draw here. I'll use this screen. Okay, so, I'm going to draw, this is sort of a very rough sketch of that beam. Now what I can do is I can take equilibrium cuts. So I can, for example, take one here, and then what I have is this, plus some resultant force here on this other side. Because these have to still be in equilibrium, we can do the sum of the forces in the x, the sum of the forces in the y, and the sum of the moments. It means that at this location, the shear stress magnitude has to be equal to the same as at this location. Left and right-hand side have to be the same. Or actually equal and opposite, right? And same in magnitude. So I made that arbitrary cut here. Well, I could have made that arbitrary cut here. I could have made that arbitrary cut, and I can make that argument all the way up to this point here. And so just, a fraction of a hair away from that rigid wall, if I took that cut, now that's the boundary, I would find that we have to have that result, that the integral on that surface still has to be equal to P in order for there to be global equilibrium, sum of the forces in Y equal to 0.
Okay, so then on the slide it said it was negative P, so would it be positive P then if we're doing resultant, or do we just assume it's still in the same direction?
Yeah, so you have to be a little careful how you do those. So the actual resultant you draw in the positive direction, although the shear stress that you draw, because it's on a negative face, you draw in the negative direction. And so if you're really attentive to your positive and negatives, then as I had noted it in my calculation, is how it's going to end up.
Okay, thank you.